First they will ask you about this paramagnetic, diamagnetic, magnetic movement, this thing. And then next they will ask you about how many unpaired electrons are there, just based on electronic configuration only now. Okay, the next question you can see. So these E naught potential values I will tell you, based on, this is also based on mostly on electronic configurations only. We know half filled electronic configuration is more stable, full filled. So it means elements during the reaction what they will do, they try to be in their stable oxidation state, okay, based on that. See again they are asking about permanganate, potassium permanganate, what is the color of it? Pale pink. Why it is pale pink they are asking? Because here it is D plus 7 electronic plus 7 oxidation state, so d orbital is empty, to that oxygen will be donating electrons, so it means oxygen is called like ligand. What I am saying, ligand. Metal is having zero vacancy now, like you will be studying about ligands in metal complexes next chapter. Anyways, I hope you know little bit about ligands. So what is the charge on oxygen? -2. What about metal here? Plus 7. So here plus 7 means how many d electrons are there? Like d0, 4s also 0. So empty orbitals are there now, 0 0 means, okay. Now from this charge, like this negative charge electrons are donated into this empty orbital. So how electrons are transferring? From a ligand to metal electrons are transferring. So what is the reason for color? See, generally color is due to electronic transition. So electronic transition may happens in d orbitals. Sometimes if there is no electron in d orbital, we may see electronic transition from where to where? From ligands to metal, or from one metal to another metal, like that. So here from where to where it is going? From one oxygen, like from ligand to metal. So you simply say it as LMCT. So this phenomenon is called charge transfer. What is it? Charge transfer. From where to where it is transferring? Ligand to metal. So in the short form what you can say? Ligand to metal charge transfer. So what is your answer for this? Charge transfer from where to where? Not all the times it is DD transition. Don't say every time DD transition only. In order to show this DD transition, they should have some d electrons now. Does it have any d electrons? So no DD transition in this case, like that. Okay. Then next, this is also, I will tell you about this again. Wait. See, they are asking about which is oxidizing, which is reducing. Again, simply based on what? Their half filled, full filled electronic configurations. Okay. What about this one, KMnO4 in acidic medium? From where to where it changes? Plus 7 to plus 2. Plus 7 to plus 2. Here they are asking about faintly alkaline or neutral medium. Plus 7 to? Where we studied this? In redox reaction. Na? So same question they are asking. So what is your answer? C. Okay. Next. This one. Hafnium having similar atomic size, because the only reason here when they ask about sizes means it should be lanthanide contraction. Okay. See. Okay, we will come back to this again. Again, see, again spin only magnetic moment value. How do you do that? Root over? Yeah. Next, this one. Maximum oxidation states. Just look at their number of valency electrons. Based on that, we can give which is having maximum highest oxidation state. For example, manganese. In 3D series, how many electrons are there? Like, I mean, electronic configuration you know now, from scandium to zinc. So now tell me for manganese, what is the electronic configuration we have? 3D5, 4s2. All that 7 electrons will be removed from manganese. So it will show maximum oxidation state of how much? Plus 7. So metal with highest reveals a maximum oxidation state. Which one is that? Manganese. Like that, things that you know little bit about, I mean, from this chapter, from based on that also you can solve these questions. Okay. Next. What about this catalyst? Have you seen? See, you have studied about contact process, Haber's process. So V2O5, where do we use that? Sulfuric acid preparation contact process. Next, this one, what is that catalyst called? Ziegler-Natta catalyst. What is that? TiCl4 trialkyl aluminium. So where will use? Polymerization. So where do we have ethylene polymerization? Okay. Next one. Yeah, based on that you can answer anyways. This one, see, oxidation of ethine to ethane. again ethanol. So this is, we'll use PDCl2, okay. So PDCl2, along with this we'll also use copper chloride like CuCl2 also, okay. I think this is also you studied for 2 marks question, I don't know whether studied or not. Interstitial compounds, not studied. See, again based on what? Electronic configuration. Like coinage metals means copper, gold, silver. Again here they are asking about colorless. Now you told na DD transition. Now check here. Why here we are saying DD transition? Yeah, all of them are having d electrons. I mean just check, like Fe+2 means what is the electronic configuration? First of all, that's why I am asking, first you need to know electronic configuration. So atomic number is how much? 26 now. So 3d6, 4 is 0. 4 is plus 2 now, remove that 4s electrons. Now what happens? 3d6, 4 is 0. So 3d6 now, so d electrons are there. Now scandium you check, scandium 21, 3d1, 4 is 2, plus 3 means remove all that electrons. See, scandium 3d1, 4 is 2. See 21 now, you always put this 2 in S, this one here. If it is titanium, you are writing it as 22. Now tell me, 3d2, 4 is 2. So based on that also you can just remember. Now I am saying plus 3. So plus 3 means how many electrons you can remove from here? All 3 electrons. So if we remove all 3 electrons, do we have any valence electrons in the scandium? So if no valence electron, will it show any color? No. So if it is not showing color, so what will be your answer for this question? Scandium. So purely what? Based on simple electronic configuration. Now you check for other elements, they have at least 1 electron. Check D5 here. This one, scandium, titanium means D. So 3d1 we have. So it will show electronic transition. Okay. So that's it. Next. Okay. This one. I will tell you again. Back to this. Okay. Now what are the elements we have? Scandium 2, scandium, titanium, vanadium, chromium, manganese, ferrous, copper. I think we have already written 2 times these periodic table elements, all their electronic configurations also, I think. Did we written? Yeah. So you just check in periodic table, we discussed, I think so. Okay. In basic class also we discussed. I think now it is not required again. Okay. So just remember, from weight to weight 3D series starts from 3D series is from 21 to 30. 4D series is from 39 to 48. 5D series is from 80. So what is the 80th element? Mercury. So what is this group elements? Zinc, cadmium, mercury, copernicium. Copernicium again 112. Okay. Now the 6D series, tell me from where it is? 89 comma actinum, this is 104 to 112. That's it. Okay. Remember these numbers. Okay. So now, what are the series elements we have? Like something like 3D, 4D, 5D. Okay. So now down the group, what happens to the size? Size. So from 3D to 4D, who is bigger? 4D. After 4D, it should be 5D. It should be like this. But when it is observed, it is something like 4D is almost equals to 5D. So what is the reason for this? This is incorrect. So this is correct. This is down the group. What is the reason for this? Lanthanide contraction. What do we mean by lanthanide contraction? See, for example, you tell me 3D series elements like scandium, and the 4D series element is what? Yttrium. This one? Lanthanum. Okay. After this, you tell me here, these are 3D, 4D, 5D. So titanium, zirconium, hafnium. Okay. Now tell me what will be the size orders for these elements? Scandium equals to lanthanum. Okay, just write this and cross it. For these elements you tell me? Titanium, zirconium equals to hafnium. See, lanthanide contraction means it is due to involvement of lanthanide elements. What is it? Due to involvement of lanthanide elements. Lanthanide elements involves after this lanthanum. After this lanthanum. It means lanthanide contraction is not applicable for this series. Which series? This is scandium series. Because after this only lanthanides are coming now. After 57, then it is coming like this is, I mean in between this we are seeing like 58, from 58 it is starting like lanthanides are starting. It means lanthanide contraction will applicable for this or not? No, right? So it means these elements order will be as like normally whatever we see, scandium less than yttrium less than lanthanum. So here in this series what you can say, no LC. Why no LC? No lanthanide contraction. Why no lanthanide contraction? Because lanthanides are not involved here. After this element only we are getting lanthanides. So it means that will be seen here. Or what is the next element we have? Tell me. After this, titanium, vanadium, niobium, Nb, niobium, tantalum. Okay. So now in this series you tell me what is the order? Vanadium less than niobium, tantalum. So you got from where it will be applicable? From this titanium series only lanthanum, like lanthanide contraction is observed, not for this scandium series elements, like see this family elements. Okay, write these two orders. Due to what? LC, lanthanide contraction. Okay. Now if they ask you about ionic radii, ionic radius. So ionic radius means same, like here you have written atomic radius. I am asking about ionic radius. For example, scandium plus 2, next scandium, titanium plus 2, like this. If they mention same charge, what I am saying? Same charge. So for ionic radius also follows same, same as atomic radius, radii, in which case if all of them have same charge, Okay, next one. But if different charges, it depends on size, like different charges, it depends on charges now. For example, scandium plus 2, scandium plus 3 is there. This is over. Now tell me here, more positive charge? More positive charge? More nuclear charge, now more positive charge means what happens to size? Size decreases. So which is greater here? So this, like this we have written nuclear charge inversely proportional to size. So more nuclear charge means what? More positive charge, smaller is the size. So they will give a question like this. It is asked previously. Mn plus 2, Mn plus 4, Mn plus 7. What is the answer? Plus 7 is the smallest one, right? Okay. Next one, what about ionization energy? First series, like 3D series elements you take again. Tell me, as per your understanding, which should be having highest ionization energy? Scandium or zinc? Zinc will be highest. Why zinc will be highest? Because 3D10 4s2. So fully filled electronic configuration, no? Okay. So due to that reason, which is having highest ionization energy? Zinc. Okay. So zinc, it means you can write like this, left to right. Again, what about size? From here to here, what is the smallest size element? Nickel, right? Okay. It means from here to here, IE value increases. Can I say increases like IE2 means what to check? Second ionization energy adugute deనికి చూడాలమ్మా? Cr plus కి. ఇక్కడ కూడా Mn plus కి. ఇప్పుడు చెప్పండి. Take its electronic configuration. 3d5 4s0. For this one 3d5 4s1. Now from where it is difficult to remove? Half filled electronic configuration, no? So due to that reason, chromium. So this is important point again. You can expect question from here. Write these 2 points. Yes, ma? What? Okay. Exactly, you can make order based on this other ways. 3D series, first ionization energy if they ask. See, which is having highest value? Zinc. Okay. So now tell me based on that, zinc first. Next? Copper. Just check values. First this one, next iron. Next cobalt. Exact values you check. Nickel. Next manganese. See, first zinc. Next ferrous. cobalt first, next ferrous, next 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 6, next next okay. So you write exact order in this way only now. Okay, because it is just based on what? Exact values. So based on exact values you will get like this. It means not only electronic configuration, there are some other factors also which is deciding their ionization energy. First factor is size, next factor is electronic configuration. Okay. So which is highest one? Zinc. Only write IE1 order. Done up to here. Just write IE1 only, don't write the values, write the order. Okay. After this, done. Okay. Next look at this. Due to availability of number of d orbital electrons like 1 to 10, we can expect different oxidation states for the elements. Okay. So now for 3D series, what is the highest oxidation state possible? +7. Okay. So why? Because it have 7 valency electrons. 7 valency electrons in manganese, so it can show highest oxidation state of how much? +7. Okay. Now for other elements you check. For copper, what are the two possible oxidation state? +1 and +2. For zinc, only one oxidation state, that is +2. And iron, mostly it will be like these are the possible oxidation states, but it will only exhibit most of the cases +2 and +3. We will see compounds like FeCl2, FeCl3, only these two oxidation states we will see most of the cases. Okay. For scandium, what is the only oxidation state possible? +2, +3. Okay. So now what is the use of knowing oxidation states? Greater the oxidation state, more is the acidic nature of that compound. Particularly, we can see a question like this: Mn2O7, Mn2O3. What is the oxidation state here we are getting? Here it will be +7, here it will be +3. So which is having greatest acidic character, they will ask. Both of them are oxides. Which oxide is having more acidic nature, they will ask. So what to do? Just check their oxidation state. More oxidation state, more is the acidic character. Write this example. Okay, just write this one. Okay, so now what are the manganese family elements we have? I mean manganese are chromium mutate, chromium. Next, molybdenum, tungsten. So now what is the maximum oxidation state shown by chromium? +6. It means molybdenum also +6, tungsten also +6. Now within these compounds, like what are the oxides we can have, like see dichromate ion is there, Cr2O7 2 minus we have. Similarly I can write for tungsten also with the same oxidation state. Okay, out of that which is more stable they will ask. See here dichromate ion in acidic medium is a strong oxidizing agent. See what happens to the stability of these oxides down the group? Stability of molybdenum oxide and tungsten oxide is greater than chromium. So down the group +6 oxidation state stability is more for which elements? Tungsten. So tungsten greater than molybdenum. It means if these are more stable, a stable compound will not react. Yes or no? A stable compound will not react. So I am giving you like oxides of this +6 oxidation state. So which is more reactive I am asking. What is your answer? Chromium. So due to that reason, okay, due to that reason chromium will be used as chromium like dichromate ion is used as oxidizing agent. How we are using? Oxidizing. Whereas these two like oxides like molybdenum and tungsten were not used. Why? Because those are stable oxidation states for them, but for chromium +6 is unstable. So that's why it is showing what type of nature? Oxidizing nature. Okay, write this. Stability down the group increases for a particular oxidation state or higher oxidation stability. Higher oxidation state stability increases down the group down the group. It means chromium +6, next what is that? Molybdenum +6, tungsten +6. Which is more stable? Tungsten. So Cr2O7 2 minus is a oxidizing agent but MnO3 molybdenum oxide and tungsten oxides are not. So what happens to oxidation states? Higher oxidation states down the group increases. Okay. Then up to here. So what are the two oxidation states shown by copper? Like what is electronic configuration? You have written 3d10 4s1. So it can show what are the two possible oxidation states we seen? Cu +1, Cu +2. Based on their electronic configuration, tell me which is more stable you will think? +1 or +2? +1. +1. Why +1? Because it has 3d10 4s0. 4 is 0 in +1 oxidation state. Okay, due to that reason Cu +1 should be more stable. But in aqueous medium, medium due to high hydration energy. What is that? Due to high hydration energy. Cu plus 2 aqueous is more stable than Cu plus 1 aqueous. So in which one? In aqueous medium, what happens to the stability order? Cu plus 2 is greater than Cu plus 1. What is the reason? Hydration energy means if we place this ion in the water, what happens? Water molecule will surround these ions. Okay, when they are surrounding, more amount of energy is released. So it will be released more in which case? Cu plus 2 case. So more amount of energy is released by hydration. That's why the stability of Cu plus 2 is more than Cu plus 1. Okay. Next one, we can see questions on this thing, magnetic moments. So what happens? Magnetic moment increases with increasing number of unpaired electron. So how can you calculate magnetic moment? Mu equals to root over n into n plus 2 Bohr magnetons. Okay. So just see, if you observe these values, if 0 unpaired electrons, 0. So now if 1 unpaired electrons, 1.73, 2 unpaired electrons, 2.84, 3, 3.87. Now if you observe like that, 5 means 5.9, 4 means 4.9, like 4 number of unpaired electrons means how many? 4.9. 3 means again 3.87. It means you just take the respective value. For example, you get 3 unpaired electrons. So how can you remember now? Around 3.8. Just check. 3 unpaired electrons, 3.8. So for example, now I am giving you one random example. Tell me. Fe plus 2. What is the magnetic moment I am asking? How many unpaired electrons? What is the valence electronic configuration for this? 3d, 6, 4s, 0. Now how many unpaired electrons? So write it in the orbital representation like this first. Fill that. 1, 2, 3, 4, 5, 6. So how many unpaired electrons? 4 unpaired electrons means mu is equals to root over 4 in, like n into n plus 2. How much? 4 into 6. 4 plus 2, 6. It is root 24. So root 25 is 5. Root 25 is 5. So root 24 now. So 4.9. So just take, if number of unpaired electrons 4 అనుకోండి, అది 4.9. 3 అనుకోండి, 3.8, 3.87, 2 అనుకోండి, 2.8, like that. 1 అనుకోండి, 1.7 or 1.8, like that you will get. Okay. You just tell me for Ni plus 2. Two unpaired electrons. So how much? 2.7, around 2.8 you can remember. So 2 unpaired electrons, 2.8. Which one more? 1 point? Okay. Next, color properties. So what is the reason for color property? DD transition. First reason is DD transition. Okay, we'll see that. So you just write these elements and their colors directly. You can expect a question from this. Cobalt plus 2, what is the color it will show? Pink color. Nickel plus 2. Copper plus 2. Like you are seeing blue vitriol, no? Just blue vitriol means what is the formula? Like CuSO4 dot 5H2O. What is the color? Color of that salt? Blue color. So Mn plus 2, what is the color? Light pink. Chromium plus 3, green. Titanium plus 3. Just remember this color. You can see direct questions on these colors also. So what is the next reason I told you just before the charge transfer? Charge transfer. So Cr2O7 2 minus, what is the color? Potassium dichromate. Potassium dichromate. This one. See what is the oxidation state here? Plus this one. For chromium, what is the oxidation state? Plus 6 you will get here. See, if it is chromium plus 3, it is green. What is this? Potassium dichromate plus 6. What is its electronic configuration? Chromium plus 3 annam anukondi. So you can get here 3d5 4s1 in atomic form. Plus 3 means it becomes 4s0 3d3. So here we have d orbital electrons. So these d orbital electrons, transition takes place from 2 levels will be there. Let us say this is one level, this is another level. From here to here electron transition may takes place. That results to give you green color. In which oxidation state you are seeing? Plus 3. No, but here what is oxidation state? Plus 6. So do we have any d orbital electrons? So d0 now. So in case of d0, it means d orbital with 0 electrons. Some compounds show color. What is the reason for that nature? That is what? Charge transfer. Okay. So charge transfer from where to where it takes place? From here, if you say oxygen, what is the charge you are seeing? -2. See, small oxygen atom with -2 charge. So it will not hold this more negative charge. What it will do? It will transfer its electron to empty d orbital of chromium. So that transition will give you the color. So what is the color of this compound? Orange color. What is that? Orange color. Potassium dichromate. What is the color of potassium dichromate? Orange color. Similarly, this one, KMnO4. You did titrations now. Violet color or purple color you are seeing. So what is the oxidation state here you will get? +7. See, if you observe in this, what is the oxidation state you have? +2. In +2 it is light pink. But in +7 it is how much? I mean purple. So purple means, what is the reason again here also? Charge transfer. Okay, so ligand to metal. Charge is transferring. Okay. Now if you see this D block elements, they form complexes. What they form? Complexes. So for example, here I have written iron complex. So complex means what it contains? Like see, we will be writing it in a square bracket with one metal atom around it, it will be surrounded with some ligands. So that ligands, how many ligands are there, that will be indicated here, number. So this number is called what? Coordination number. How many ligands are present in a complex is indicated with what? Coordination number. So if this complex have any charge, that we are writing here as a charge, like it can be plus, minus, something like this. So now what is the reason for this? Compounds in which metal atom ion bind to the number of anion or neutral molecules by sharing electrons forms a complex. See, metals, what is the charge? Generally they are, metals means electropositive charge, like positive charge will be there. So now ligands means what they have? Either they have lone pair electrons, for example ammonia I am writing, what they have? Lone pair electrons. Otherwise chloride ion I am writing, what is the charge it has? Minus. So this electron density will be donated to the metal ions. Okay. So now who is donating electrons? So both for bond formation, both electrons are coming from where? From ligand only. So from between metal and ligand in the metal complexes, the bond will be what type of bond it is? Both electrons are given by one atom only. Both electrons are given by one species. Coordinate, covalent bond, or you can simply say it as dative bond. Okay. So in metal complexes, what type of bond formed? Coordinate, covalent bond. Okay. So now we have a specific separate chapter for this metal complexes, like metal complexes. In the next session we will discuss about that. So again tell me, how can you find oxidation state in the metal complexes? Consider them separately, like iron as separate, cyanide, Sn is there now, what is the charge on each cyanide? Minus, cyanide ion you will write. How many are there? 6. So each minus 1, what is the overall charge present? Minus 3. So from this, what is the charge oxidation state of iron? Plus 3. Okay, like that we can expect just finding oxidation states for different complexes also. Okay, can you tell me for this one? Platinum tetrachloride complex is there, plus 2. How much it is? See. Okay, Cl is minus 1. Okay. Next tell me. Platinum is how much? Plus 2. See, you know, cisplatin, there is a compound called cisplatin. Where it will be used, tell me? Like this we are writing. So what is this compound called? Cisplatin. It means platinum will be the central atom. How many chlorines are there? 2. So the 2 chlorines will be same side, and 2 ammonia molecules will be same side, like this. See, we know if same group same side, what we can say? Cis. And platinum same group same side, so what I can say, this is cisplatin. So it will be used in cancer treatment, where it will be? Okay. So transplatin means how it will be now, tell me? Platinum, like here one Cl, here one Cl, here one ammonia, like opposite. So this can be trans, this can be cis. So which is used in cancer treatment? Cisplatin. Okay. So now coordination compounds have very vast applications in medicinal chemistry, industrial chemistry. Okay, this one is done. Okay, and also hemoglobin contain what? 4 5 rings. At the center what we have? A metal, iron. Okay, so now what is a, like, how many nitrogen atoms are surrounded around the iron? 4. So we can say like this, if you see, what is its coordination number, I can ask. How many bonds you are seeing? 4. Again, downside what will be attached? Okay, we'll see in the next class. Okay, and very famous test that you performed in the lab is what? Brown ring test. So tell me what you did in that during the test. For what purpose we'll do the test? Tell me first. Confirmation of? How you can confirm that? Tell me. So we'll take freshly prepared FeSO4. To that nitrate solution, we will add freshly prepared FeSO4. After that, we'll put it in a tilted manner and we'll add sulfuric acid. Okay. Now what happens? It will forms a brown junction when you are adding this sulfuric acid. Now what is the compound formed? That brown ring complex, the black color one, what is that? Fe, H2O 5 times, NO plus 2. Okay. So this is a complex you are going to see. What is the complex formed? Fe, H2O 5 times, NO plus 2. Okay, you just write the formula of complex. Tell me more. This is plus 1, you write more. What is the charge on that? Plus 1. So because x plus 5 into 0 plus 1 equals to plus 1. Okay, write plus 2 only. So what is the oxidation state of iron, they will ask in brown ring complex. This is a question asked previously. What is the oxidation state of iron in brown ring complex? See, instead of giving like this, they will give the formula like this. Sulfate ion they will mention. What is the charge on each sulfate ion? Minus 2. It means our complex should have plus 2. Now tell me what is the oxidation state of iron in brown ring complex? See, what about water molecule? It is a neutral or any charge? So neutral means 5 into 0. What about NO here? NO is a positively charged ligand. What is the charge on NO? Plus 1. Okay, it is plus 1. Now calculate for iron. This is x plus 0 plus 1 equals to plus 2. So oxidation state of iron in brown ring complex is plus 1. Remember this is the important point again. Okay. So how many d orbitals we have in the d subshells? 5 d orbitals. How can you represent them? Like dxy, like dxy, dyz, dzx, this one dx square, y square, this one dz square. Okay. So now these three things, first dxy, dyz, dzx is nothing but you are taking two coordinates. Let us say this is x coordinate, y coordinate. xy means that orbitals are lying between x and y. So now they will ask what is the angle with the d orbital is oriented in dxy with these coordinates. What is the angle it is making? 45 degrees. So it's a very simple question, but you need to answer it. See, here it is now. So what is the angle you are making? See, this is 90, it means half of it. So you will be seeing 45 angle in what are the cases? In first three cases it will be 45 degrees. And what about here dxy, y square, in this case? It will be like this now, and one more will be like this. So what is the angle here you are seeing in dx square, y square? 90 degrees. next one. See, next thing is interstitial compounds. We have seen a question on interstitial compounds. So what is that means? We know like D block elements are metals. So if you observe like their structure, metallic lattice, it means like metal atoms will be arranged like this, like this, like this. So there is a small gap between the metal atoms if you observe. So in that small gap, some gases will be accumulated. What I am saying, if you take a platinum surface, platinum is a metal, no? So in that surface small holes will be there. Okay, in that holes if you pass hydrogen gas, that hydrogen gas will be accumulated. So now which gas you are passing? Hydrogen gas. So it will form interstitial hydrates. What it will forms? Interstitial hydrates. See, this is a metal lattice. So these are some interstitial atoms, means let us say oxygen, hydrogen gas is passing. So in these small gaps, what will be accumulated? H2 gas. Then you can say that as interstitial hydrates. Like that, if you pass carbon vapors, it will forms carbides. Okay, interstitial carbides you can say. So now due to this reason, when they form interstitial hydrates, carbides like this, see, interstitial compounds are formed when small atoms like carbon, hydrogen, nitrogen are trapped inside the crystal lattices of metals. We are going to get interstitial compounds. For example, if I pass carbon, we will get carbides. Nitrogen gives nitrates. Hydrogen gives hydrates. Okay. Now, interstitial compounds are considered to be non-stoichiometric. What I am saying? Non-stoichiometric. What do we mean by non-stoichiometric? See, generally, if I write a compound like ammonia, I am writing. See, there is a fixed number of nitrogen atoms, hydrogen atoms. But if you see interstitial hydrates, like one vanadium is there, but hydrogen is something like a decimal number you are seeing. Is this a fixed number? No. So these numbers varies depending on the amount of gas you supplied. So we can say them as what? Non-stoichiometric compounds. Which are non-stoichiometric? Interstitial compounds are non-stoichiometric. Okay. So what you can write? Interstitial compounds are non-stoichiometric compounds, you write. And now their properties. If you see these properties, when you compare with a pure metal, what I am saying? A pure metal, for example, pure titanium is there, and now its titanium interstitial compound is there, like this. Now comparing titanium and its interstitial compound. So now what it is saying, see, high melting points. When you compare with the pure metal, which is having higher melting point? Interstitial compounds. When you compare with the pure metal, interstitial compounds are harder. When you compare their chemical properties, like physical properties also, so they retain their metallic conductivity. So both of them are having same metallic conductivity. What about their chemical nature? They are chemically inert. So you just write these 4 points. What are the 4 points? First one is they have higher melting point than respective metals. They are very harder than respective metals. They retain conductivity. Next, chemically inert. Done? Okay. previously I explained about oxides. What happens with increase in oxidation states? Acidic nature of oxides increases. Okay. Now you can compare 3 oxides like V2O3, V2O4, V2O5 and CrO, Cr2O3, CrO3. Okay. So now just find their oxidation states. Which is highest here? +6. So +6 one is acidic. Lowest oxidation state is basic. Intermediate oxidation state is amphoteric. Okay. You write these 3 compounds. These 3 compounds and their acidic basic characters. Okay. Oxidation states increases and acidic character also increases. So again for vanadium, if you see, V2O3 is what nature? More basic. V2O4 is basic, less basic. V2O5 is amphoteric. So for vanadium, do we have any acidic oxide? See, for a particular oxide, like for a particular element, vanadium, what is the maximum oxidation state vanadium can exhibit? Tell me. Vanadium, what is the atomic number? Scandium, titanium, vanadium, 23. So 2 plus 3, 5. So maximum oxidation state can be shown as +5. So +5 oxide of vanadium is what now? Acidic or amphoteric? Amphoteric. So do we have any acidic oxide for vanadium? No? No. So what is the color of potassium dichromate? Potassium dichromate. Orange color. Okay. Okay, done these 2 orders. Okay, next one, listen here. What is the color of potassium dichromate we discussed? Orange color. Okay. So we can call it as dichromate. What it is? Dichromate. So here oxidation state is +6. Here it is called chromate. How many chromiums are there? 1. So you can call chromate. Here also oxidation state is +6 only. Okay. Chromium maximum oxidation state is how much? +6. Okay. But in acidic medium, in which medium? Acidic medium. This solution, chromate converts into dichromate form. To which form? Chromate to dichromate. In basic medium, dichromate converts into chromate. So it means you are going to see the color change. If it is in basic medium, what is the color you are going to see? Orange. If it is in acidic medium, color will be yellow. So you write like this. Here you can write yellow and here it is orange. So in basic medium, what is the color? Orange, because it is existing in which form? Dichromate form. In acidic medium, it exists in chromate form, color will be yellow. Okay. So now where you are going to see this in your daily life? Dichromate application. See on the roadside we will see like traffic police uses breath analyzers if you observe. Drunk and drive checking ki vaadtara leda? So it contains dichromate. What it contains? Dichromate. Okay. So now this dichromate, when it is detecting alcohol from that person, it shows color change in that machine. By looking at the color change, he can identify whether that fellow is drunken or not. Okay. Now intensity of that color also changes. If you drink more alcohol, intensity of that color will be more. Based on that, he will identify whether the person is drunken or not. Is this done up to here? Yeah, it is something like this. Previously, what is that color? Orange. So if it is detected, it is going to be green. So the intensity of green color says that whether the fellow drunken or not. Okay. Next one. So do you remember this compound? CrO5. What is the oxidation state of chromium? +6. What is the structure it has? CrO5. Blue butterfly I told you, if you remember. So how it will be? CrOO. It will be like this. Normally if you calculate, how much you will get? +10. But this is incorrect because it exists in this form, because oxidation state of a element cannot cross its maximum valency electrons. How many valence electrons for chromium? 6. So the maximum oxidation state of chromium can be 6 only. Okay, so that's why we got this structure. Okay, now this compound is unstable, and what is its color? Blue color. Okay. Like this you can understand. How many peroxy bonds are there in the compound? Peroxy bonds. Peroxy bond. This side one peroxy bond, this side one peroxy. Now what are the types of oxygen present in the compound? -1 one oxygen with -1, like that. How many are there? 4. So 4 with -1 oxidation state, 1 with -2. So there are how many types of oxygens now? 2. One is -2, another one is -1. Okay, next. Now the structure of potassium dichromate, K2Cr2O7. Cr, you just put it like this. How many oxygens are there? 7. One here, one more here. Next what I am doing, C check once here, one more here, this side, 4 over. But how many are there? 5 over 6. Okay, but chromium, you tell me how many bonds it can make? Maximum 4, maximum 6, but already 6 over this one and this one, but still we have one more oxygen. If I want to insert that, it becomes a 7th bond. So now what to do is, K2 is there now, convert this into O minus forms. O minus, K plus, K plus. Next, still how many bonds we can put on the chromium? One more. So you put one oxygen like this. Okay, so if you observe, there is a middle oxygen and surrounding oxygens are how many? 3 on each of these. See, pi bond, sigma bond, negative charge. Can I say that conjugation is there in this system? Okay, so if it is shifting, become pi bond, and this will become sigma bond. Okay, like that. This one also can conjugate. So it means all these terminal oxygens are of same. Can I say all these terminal oxygens are same? So due to the conjugation, all these terminal oxygens are same. These terminal oxygens also have same story like this. So these are also same. It means all terminal oxygens of this chromium are same. How many are there like that? 6 oxygens are same, and the middle one will be having different, because it will not involve any of these conjugations as we seen here. Okay, so you can expect a question like this. How many types of oxygens are there? Okay, or how many types of bond lengths the chromium having with oxygens? See, due to the conjugation, 1, 2, 3, all these are equivalent. ఇవన్నీ కూడా సేమే, ఇవి కూడా అన్నీ కూడా సేమే, అంటే ఈ బాండ్ లెంత్ కూడా సేమ్ అవుతుందిగా. సో దిస్ బాండ్ లెంత్ ఆర్ సేమ్. సో 6 oxygens, 6 chromium oxygen bonds are, bond lengths are same. This middle one is different, that Cr, OCr bond length is different. Okay, this all terminal chromium oxygen bond lengths are same for this one, this chromium also, but these two bonds are different from terminal ones. Next, what is the hybridization of each chromium? What is the hybridization of each chromium here? How many sigma bonds are there? 1, 2, 3, 4 sigma bonds. So generally we will say sp3, right now, but chromium has what? Only d orbital in the valency. So you should say it as sd3. What is that? sd3. For this chromium also it is how much? sd3. Okay. Same thing with manganese, like KMnO4 minus. So in this case what is the oxidation state? +7. How many manganese are there? Oxygens are there? Put like this. Now how many sigma bonds are there? 4 sigma bonds. 4 sigma bonds means again sp3, or you can say sd3. Now sp3 means what is the structure we will get? sp3, what is the structure? Tetrahedral. So here also it will be tetrahedral. So in this case also each chromium is, what is the structure you will get? Shape tetrahedral around each chromium, you can remember. Okay, next. Okay. Can you balance this reaction? Can you balance this reaction in the fast way? Yeah. How can you balance this fast? 2CO2. What is the steps I told you? First find their oxidation states. What are the oxidation states we have here? How to calculate? So you will get +3 you will get. Here how much you will get? +7, +2, and here how much it is? +4. Now what I told you, when you find the oxidation state, now check how many electrons are in oxidation reaction, how many electrons in reduction reaction. How many are involved in oxidation and reduction? Check what is happening to this carbon from here to here. Oxidation. How many involved electrons? 1 for 1 carbon. How many carbons are there like that? So how much you should take? 2. Here how many involved? So 5. Are these numbers same? No. If not same, what to do? Into 2 into 5. So what happens to the equation? This one should be multiplied with which number? See here it is 2, now multiply this with 5. This should be multiplied with 2. Now tell me finally. 5C2O4 2 minus plus 2MnO4 minus gives, like H plus you write as it is. Next 2Mn plus 2. This one 5CO2 plus H2. Okay, done with this number multiplication. So equal electrons. Now check the carbons, how many? 10. There it is 5 only. So convert that into 10. Next, manganese how many? 2. There also 2. Oxygens how many? All atoms are over. Next balance oxygen. How many here? 20. Here 8. That side 20. So what I should make? 28. So here 28 are there, 20 over. So I can make it as 8. 7 plus 1, 8 it becomes. So water is 8 waters. Next 16H plus. Okay. In the same way, you just answer me for the next question. Can you balance this one? The second equation. We did it for first one. Just now we did it for this equation. Can you do this? Balanced already. NO2 converting into acidic medium. Yeah, can you try this? What are the oxidation states we have? +3, +7, +5, +2. Next, what to do? So how many electrons involved? 2 electrons. Here how many involved? So what to do now? So now what happens? This one here. 5 NO2 minus plus 2 MnO4 minus. Next 5 NO3 minus plus 2 plus H2. Next nitrogen's 5 balanced, manganese balanced. Next how many? 18 this side, that side 15. So what to do? 3 H2O. The next hydrogens are left, where I should add 6 H plus. So just check, do we got the same number? Yes. So 5 NO2 plus 2 MnO4 minus 6 H plus 2 Mn plus 2 plus, okay, 5 nitrates and 3 waters. So what are the steps? Oxidation states, find number of electrons involved in the both processes, equalize them by multiplying with the suitable numbers, or just crisscross also you can do. Okay. After that, balance all atoms other than oxygen and hydrogen. Then balance oxygens by adding water. Last, balance hydrogens by adding H plus. Okay. Okay. Next one. So now tell me again, potassium dichromate in acidic medium, how it will exist? Yellow. And what is the oxidation state? +6 only. In both cases it will be +6. So in basic medium it will be orange, acidic medium it will be yellow. Next. Now what are the F block elements we have? 2 series. What are those? Lanthanides and actinides. So what is that code what I given to you for lanthanides? Do you remember elements? Just remember elements and their electronic configuration, mostly questions from that only. What are the elements I told you? Like Lacina is pretty, something like that. I given you some, tell me. Or anyways, you remember that in the way you can, or you follow the trick. Lacina is pretty and Pramod, Samir, Europe, Gaudi में ticket देकर लिया, तुम भी ले लो. I told you that one and I told you to remember. So now what are the elements we have? Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. First one is, last one is lutetium. Now what is their atomic number? 50. Lanthanum is 57, but starts from where? 58 to 71. 58th element is what? Cerium. 71st one is lutetium. Okay. So now tell me what happens to the sizes from left to right? Size. Like left to right size generally decreases now. Okay. Next one. These are also metals now. So metals means generally positive charge they have. So all lanthanides will exist with a most common oxidation state of +3. What is the most common oxidation state? +3. So now for example sodium is existing in +1 oxidation state, means like it can form NaOH type of base, like NaOH is a base. Similar to that, lanthanides forms what? LnOH type bases. This kind of bases it will be formed. So what type of bases they will form? LNOH. For example, cerium OH tries, or lutetium OH tries. Like this we will see the basic compounds. Okay. Now what happens to size? I am saying from left to right, size decreases. So which is smallest size out of this lanthanides? Lutetium. So if it is a small size, so small size with more positive charge and OH. See, basic nature means what do we mean by basic nature? A compound is more basic means it should release OH minus. So now left to right, what I am saying is basic nature decreases. What I am saying, basic nature decreases. Why it is decreasing? Due to its small size, it will strongly binds this OH. Will it come out now? It won't come out, means it is least basic now. So which is most basic out of this? Lanthanum hydroxide is highest basic and least basic is lutetium. Okay, so what happens to the basic nature of hydroxides of lanthanides? Decreases from left to right. So highest one is lanthanum. Remember this point, it is important. Now what is the most stable, most common oxidation state we see in the lanthanides? +3. Next. Their electronic, what is general electronic configuration we will write? N-2 F 1 to 14, N-1 D 0 to 1, next NS2. Okay. So now tell me for lanthanum, what is that? Lanthanum. So it will be 4F0 5D1 6S2. See, lanthanum belongs to which block they will ask. This is D block element only, but after lanthanum what are the elements are starting? They are F block. So how many F block elements are there? 14. But if you see in the series, you will be seeing 15, but this lanthanum belongs to which one? D block only. Okay, right. Next one. So what about actinides general electronic configuration? 5F 0 to 14, 6D 0 to 2, 7S 2. What is this? 7S 2. So these are the two general oxidation, what is this? Electronic configurations you remember for lanthanides and actinides. Okay. So the remaining series, things about lanthanides, actinides we will discuss, continue in the next session or evening session.